Swayam Prabha. Digital India. Educated India.
Let us come back to the in continuation of those chirality, the projection formula. So far we have covered stereoisomerism and then the different formula, perspective formula that are used to depict the three-dimensional molecules into a two-dimensional plane, and the rules associated as in changing the formula in the two-dimensional plane. The first lecture, we introduced the concept of chirality. Okay. Now, it may sound that we am repeating the whole thing again, but it is not a repetition, because the concept of chirality kept evolving. As I told you, kept evolving means initially something was said and then it has to be revised. Initially, the definition of chirality was that it has to have a chiral center, that means a carbon with 4 different groups. Then, because of the presence of mesotartaric acid, people found that even when chiral centers are present, they may be optically inactive. So, they are not chiral. And the third problem, I gave you one example yesterday, multiple examples will be given in subsequent classes, where we can show that there are molecules where no such carbon atoms are present, but the molecule is chiral. So, the problem was actually associating the chiral center with chirality, and it was Mislow, a very famous stereochemist, along with Eliel and others. They are all famous scientists dealing with stereochemistry. They actually dissociated this concept of chiral center association with chirality. They said that chirality has nothing to do with the presence or absence of chiral center. It is the symmetry criterion which dictates the chirality, and we have gone through what are the symmetry criterion. We said that the molecule has to be disymmetric in order to be chiral. What is disymmetry? Disymmetry is devoid of the I, the sigma and the s axis. Okay. Now, by the way, these are called improper elements of symmetry. So, the molecule has to lack improper elements of symmetry in order to show chirality. What about the proper axis of symmetry or the proper element of symmetry, which is called the C axis, the simple axis of symmetry? I said that that may be present, that may not be present. Okay. So, that is why if I do a statement that all disymmetric molecules are chiral, that is the correct statement. All asymmetric molecules are also chiral, that is also a correct statement, but to have chirality, asymmetry is a must, is not a correct statement, because you are introducing another extra parameter, that is the C axis. Okay. Now, that means that there are molecules where C axis is present, but the other improper elements of symmetry are absent and they are chiral. So, what is the simplest example? The simplest example is this tartaric acid molecule. If you look at this tartaric acid, the Fischer projection of an optically active form of tartaric acid. Okay. This does not have any I axis, this does not have any S axis, this does not have any sigma. So, it is optically active, but it has a C2 axis, because if you put an axis here and you rotate it by 180 degree, remember just now I have said that Fischer projection formula can be rotated in plane by 180 degree. So, if you have an axis like this and you rotate the molecule by 180 degree, then what you get is the same molecule. So, this molecule has a C2 symmetry going through this point vertical to this plane of the board. You rotate it by 180 degree, which is allowed in Fischer projection, you get the same molecule. Okay. So, it has got a C2 symmetry. So, it has got C2 symmetry, but it is optically active. So, this is the very simple example of a molecule, a chiral molecule possessing a C2 symmetry. Okay. So, there are plenty of examples like that, where C axis is present, but the molecule is chiral. But I wanted to just show you a very simple example about this concept, that why C axis was ultimately excluded from chirality. Okay. Now, again what happened, this chirality, when a molecule is chiral, the general notion that comes into our mind that it is chiral because there is some point of chirality in the molecule. Actually, that originated from the again the same misconcept of a chiral center attached with 4 different groups. Again I repeat what I said, that when I say a molecule is chiral, it as if it means that there is something in the molecule which is responsible for the chirality. Okay. But chirality, when is the what Mislo said is that a chiral molecule, when I say a molecule is chiral, in totality it is chiral. There cannot be any center in the molecule which is only chiral and the others, the rest are not. It is like saying that if I wear a blue shirt, then every piece of the blue shirt is blue. Okay. So, if I say a molecule is chiral, then every point in the molecule is chiral. So, you cannot say that there is a center here which makes it chiral. Okay. So, like a blue shirt, you cannot say the shirt is blue because there is a blue point inside the shirt, the whole thing is blue. So, okay, this is what is called all pervasive property. So, chirality is a all pervasive property. So, the problem was that when we are equating this chiral center with chirality, the existence of a chiral center with chirality, already a mistake has been made, because without chiral center molecules can be chiral. The second mistake that was made is that associating that you are saying that a molecule is chiral because of the presence of a center, a chiral center in the molecule. So, that was a second mistake. So, Mislo said that the carbon atom where there are 4 different groups which are attached, you cannot call them as chiral center, because that is causing some misconcept in the minds of the student. The student thinks that because there is a center, as I said, because there is a blue center, the whole piece of cloth is blue, that is not correct. Similarly, a molecule is chiral because there is a chiral center in the molecule, that is also not correct. So, then the question is, what should we call that carbon where there are 4 different groups? Now, the literature up till now is totally confused, because many people still say the atom which a carbon atom where 4 different groups are attached are chiral centers, but Mislo said, or the modern stereochemists, they said that that should be called a stereogenic center. A stereogenic center is a center where interchanging the position of 2 groups gives rise to a stereoisomer. Okay. Again I repeat, what is a stereogenic center? A stereogenic center is an atom which is attached to different ligands, and if you interchange the position of the groups of the ligands, you get a stereoisomer. Okay. Like suppose this is what is called maybe the tartaric acid, this is lactic acid, not tartaric acid, CO2H, CH3, OH and H. This is one particular form of lactic acid. Okay. Now, this carbon Earlier it used to be known as chiral center. Now, as I said again, people still say it as chiral center, books also write it as chiral center. So, the International Union of Pure and Applied Chemists, that means IUPAC, which is the highest board, who actually gave the nomenclature system. Then they also clarified the Kahn-Ingold-Prelog system of absolute configuration. So, what do they say? They actually took a middle path. They said that this may be called a chirality center. Okay. But as I said, at this level you can continue with the chiral center, but at the same time you should be aware of the fact that this chiral center, real pure stereochemistry people, they do not like this word. Instead, they use the word stereogenic center. They are more comfortable with the word stereogenic center. And one more reason is because the presence, when I say this as chiral center, it immediately gives a visualization that the molecule is chiral, but that may not be. As I said, in tartaric acid that may not be. In tartaric acid, mesotartaric acid, you have inactive isomers, optical inactive isomers. So, that is why they did not like this word chiral center. So, they introduced the word stereogenic center. They said that when a carbon has these 4 different groups, what it gives rise is stereoisomerism, not chirality. Chirality is an associated, an extra bona fide bonus of having these 4 different groups, but that bonus may be there, may not be there. Okay. In mesotartaric acid, the bonus is not there. That is why they wanted to dissociate. They said that presence of these carbon gives rise to what is called stereoisomerism, and the definition of stereogenic center, that means that gives, that is the genesis of stereoisomerism. That is why that is called stereogenic. If you interchange these 2 groups, what you get? H here and CO2H there. And what did I say just earlier in Fischer projection? Interchanging the groups gives you a stereoisomer, in this case an enantiomer. One exchange is not allowed. If you do that, if you do this one exchange, what you are going to get is a stereoisomer. In this case, this is the mirror image of this one, that I have shown in the earlier lecture. Okay. So, this is a stereogenic center. The definition is an atom where interchange, which is attached to different ligands. Ligands are basically the substituents or the atoms attached to that atom. If you interchange the position of 2 groups, remember 2 groups, then you get another stereoisomer. So, then that center which you are considering is called a stereogenic center. Okay. Interestingly, stereogenic center is also associated with double bonds. If you have this compound, this is what is called cis 2-butene. Now, look at this carbon. If you interchange the position of methyl and hydrogen, what will happen? You will get what we call the trans 2-butene. Trans 2-butene. And what is the relationship between these two? They are stereoisomers, but they are not mirror images. So, they are diastereomers. Okay. And what is the definition of stereogenic center? That interchanging the position of the groups gives you a stereoisomer. So, by definition of stereogenic center, this carbon is a stereogenic carbon. So, now the stereogenic carbon covers not only the earlier carbon center, the chiral center, it also covers the sp2 hybridized carbon like this. Okay. So, that is what are called stereogenic center, and molecules possessing stereogenic center with the phenomena is called stereogenicity. Okay. This phenomena of showing of interchanging groups giving diastereomers, different diastereomers or enantiomers or in general stereoisomers, this phenomenon is what is called stereogenicity. Okay. Now, as I said that chirality is an all pervasive property. That means, when you take a chiral molecule, every point in the molecule is chiral. You cannot say that there is a chiral center in the molecule. Okay. You see, the concept is very important. If you say there is a chiral center in the molecule, that means other centers are not chiral, you are saying, but that is not true. In a chiral molecule, every point in the molecule is chiral. Okay. So, every point in the molecule is the chiral, and then this scientist Mislow, and I think there is another one, his name was Siegel, Mislow and Siegel, they introduced the concept of, along with stereogenicity or stereogenic center, they introduced another concept which is called chirotopic or chirotopicity. Okay. Chirotopic or chirotopicity. Now, what is that? They are saying that in a chiral molecule, every point, as I said, every point is chiral, or they reside in a chiral environment. I can say every point is chiral. That means, every point resides in a chiral environment. And he names this as, these points are, he named it as chirotopic points. Chirotopic points. Like if I look at this molecule, first of all, whether this molecule is chiral or not. This molecule, whether this is chiral or not. Now, usually one way of, in Fisher projection, usually what we check is the plane of symmetry, whether plane of symmetry is there or not, because that is the easiest one to check. Like the top molecule, I can immediately say that it is not a chiral molecule, because it has got a plane of symmetry passing through this. This is the mirror image of this, that is the mirror image of this. So, the top molecule is not chiral, that because it has got this sigma. Okay. If you are a little bit advanced, you can say because it has got S1. Okay. This molecule, on the other hand, if you do the same operation, bisecting this molecule, you do not see that, you do not see the mirror image halves. So, this is not a plane of symmetry. Now, the another mistake or misconcept students may have is that, what about the center of symmetry? It appears that as if this wedge and this wedge, if I draw the line from here, send it backwards, I should reach to this wedge. This edge also should be like that. This is also the carbon. If I draw this and send it back, I should reach the carbon. It's the same methyl. So, as if this molecule is having a center of symmetry, but that is wrong. Why that is wrong? Because again, because of the problem that it is a two-dimensional representation of a three-dimensional formula. Okay. What is the geometry of these bonds? This is actually beta bonds. Remember, horizontal bonds are above the plane of the board, and that is called beta bonds. Okay. So, that is beta. So, if you join this and then extend it backwards, this bond should, if this bond is alpha, then it is not a problem, but because this is a horizontal bond, this is still beta. So, this is a wrong concept, because you are starting from a beta, you join this point, you should end up in the alpha position when you go backwards, but because of the two-dimensional representation, you might suffer from this misconcept. I am seeing it, this center of symmetry, but that is not there. So, it does not have any center of symmetry. It actually, center of symmetry should not be considered in Fisher projection. It always leads to different problems like this, of this alpha beta nature, because that is not shown in the projection, which one is alpha, which one is beta. So, better always look at the sigma plane, whether it is present or not. So, this sigma plane is not present in this molecule. So, this is chiral molecule. This is a chiral molecule. So, according to the definition, a chiral molecule, every point is chiral or that belongs to a chiral environment, and that point is called a chirotopic point. So, if I ask that what is this point now, this carbon is chirotopic. Why? Because this molecule is chiral, as simple as that. The molecule is chiral. So, every point is chirotopic. Okay. Now, the question is, what is the relationship between stereogenicity and chirotopicity? They are closely associated, you will see now. This is chirotopic. Now, the question is it stereogenic or not? Now, how to proceed or how to answer that? What you do, you interchange the position of two groups and see that are you getting a stereoisomer, a different stereoisomer compared to the original or not. If you get the same thing, that means that becomes non-stereogenic. Okay. So, let us do that. So, let us interchange the position of H and OH. Okay. So, this is methyl without disturbing the others. So, I interchange the position of these. This is OH, this is H, this is methyl, keeping the others intact, OH, H. Okay. So, what I did, I interchanged these two, and now my task is to see whether this is same as this or this is different as this. If they are different, then this will be stereogenic. If they are same, then they will be non-stereogenic, then that will be non-stereogenic. So, how to prove that? Now, we have one rule in Fischer projection again, 180 degree in plane rotation is allowed. So, now you do a 180 degree in plane rotation. So, I rotate it in plane, which is allowed, by the way. So, you do it. So, now if you do that, see, for beginners I will say that better you number it 1, 2, 3, 4, 5. So, if you rotate it in 180 degree, the 5 methyl will be here at the top. This is the methyl at the 5 position, the 5th methyl, and this is the methyl which was at the numbered, which at the number 1. So, where will be the number 2? Number 2 will be here 180 degree. So, after 180 degree rotation, this wedge which was in the left, that comes to the right. So, the left ones will come to the right ones will go to the left. Okay. This is the number 3, this is 1, this is 2, this is 3, this is 4, this is 5. So, now you place the groups. The wedge is this number 2 wedge will be now on the right, number 3 wedge will be on the right, because this is 180 degree rotation, and number 4 wedge which was on the right, that will be on the left. So, now you see the relationship between, suppose this is A molecule and this is after rotation, this is after interchange and then rotation. Okay. This is molecule B. What is the relationship between these two? They are same. So, if they are same, this center is non-stereogenic. So, this is an example of a molecule which has got a non-stereogenic but chirotopic center. Okay. And I can have very reverse situation. See, this molecule is an achiral molecule. This molecule is an achiral molecule. Remember, I have said that in a chiral molecule, every point is chiral. I did not say the reverse thing, that in an achiral molecule, every point is achiral. That I did not say. okay, because that has much more implications, and that gives a very wrong concept that in an achiral molecule, because in a molecule there are local environments which can create chirality locally. That is why when dealing with achiral molecules you have to be very careful. You cannot say that in an achiral molecule each point is achiral, okay. But in a chiral molecule we can always say that each point is chiral. Each point is a chirotopic point, okay. But stereogenicity, there can be a point can be chirotopic, but the center can be non-stereogenic. Now, let us come to this molecule. This molecule is achiral, okay. This molecule is achiral and it has got a plane of symmetry and passing through that middle carbon, that C3 carbon. And if a plane of symmetry, if the symmetry element passes through a carbon, symmetry, that improper element of symmetry, improper, that means I, sigma and S. In this case we are talking about sigma, it is passing through the middle carbon. So, this carbon is an achirotopic carbon, that means it is not chirotopic. So, what is not a chirotopic point? The point in which these improper elements of symmetry are passing. So, they are a chirotopic point, because the sigma plane is passing through this carbon. So, this is not a chirotopic point, this is a chirotopic point. And what is this? And now, what is the stereogenicity of this carbon? Again, to prove that, what you have to do? You do an exchange here. So, bring the wedge onto the left side and these two wedges are on the right side, methyl, hydrogen, hydrogen, methyl. Now, whatever you do, if you do the 180-degree rotation, what will happen? These two right-handed wedges will go to the left hand, onto the left side, and this left wedge will go to the right side. So, they will never match, because here actually basically all the three wedges are on the same side. You cannot do that. Now, you cannot have that situation by 180-degree rotation. So, they are two stereoisomers. So, the relationship between these two are stereoisomers or stereoisomers. Okay. So, basically now, so this carbon is what? This carbon is achirotopic, but it is stereogenic. Okay. So, that means there are different situations that can have a carbon can have. A carbon can be chirotopic and stereogenic. A carbon can be stereogenic, but achirotopic, I gave you an example, and a carbon can be non-stereogenic, but chirotopic. So, all these are possible. So, these are very important concept in this isomerism, that this shows the connectivity between isomerism and between the chiral environment that is residing inside a molecule, because we always suffer from this concept that in a chiral molecule, if I have a fluorine, if I have this molecule. Okay, so, let us again look into this molecule and the concept of chirotopicity and stereogenicity. If you look at this molecule, this is a carbon bearing 4 different groups. So, naturally this is a chiral molecule. And now, what happens to all the individual atoms here? This carbon is chirotopic, because the molecule is chiral. So, every point has to be chirotopic. This white atom is chirotopic, so as the green, so as the red, so as the blue. But what is the difference between these atoms versus the carbon atom, which is holding these 4 ligands? This carbon atom, in addition to chirotopic, it is also stereogenic, because if you interchange the position of the green and the blue or the white and the red, you get another stereoisomer. So, this is chirotopic as well as stereogenic, but all other atoms are only chirotopic, but not stereogenic. I hope this concept will be clear more as we handle more systems. Thank you very much.